So last time we had seen this lemma, which states that if you have a Galois extension, so complex numbers here, rational numbers here, and we have an extension E of Q containing C, such that this is Galois. And this is very important. The Galois group is abelian. Then for every alpha in this extension and every element of the Galois group, you have that the absolute value of the image of alpha under G equals the image under G of the absolute value of alpha. And as you'll see, this will play a role in the next result that we are going to see. But before we proceed, I'd like to give an example to show that the condition that the Galois group is abelian is necessary. So an example in which the Galois group, all other conditions staying the same, that is, we have an extension of this kind, is not abelian, and the result does not hold. And the example is well known, but let's, I mean, the extension we use is well known, but let me review it anyway. So the extension E is the splitting field so in Italian campo di spezzamento o campo di riducibilità completa of the polynomial is cube minus 2, which is a polynomial with rational coefficients. Integer actually, but rational from our point of view, that's interesting. So we know that, that the three roots of this polynomial are, say, alpha, alpha omega square, where alpha is the unique real root of this polynomial, okay? And then omega is a primitive third root of unity. Because you remember that you have, if you have two roots of this polynomial, their quotient will be a third root of unity, okay? So all these raised to the third power will give 2, because I mean omega cube is 1, okay? So this field could be given in this form. This is the smallest field containing these elements. Smallest extension of Q inside the C containing these elements. But this can be also conveniently written as Q alpha omega. This is easy to see because, of course, these three elements are here because alpha is here. Then, I mean, since this is a field, alpha times omega is there, and alpha times omega, that is alpha omega squared, is here. But also conversely, I mean, if you have these three elements, as I was just saying, if you take this times the inverse of this, you get omega. Okay, so here you have omega and alpha. Okay, so these two are equal, and writing this extension in this form is particularly useful because this implies that the order, the degree of this is 6. Why is it 6? Because you split it in two. You split it as okay, let's say, okay, you put in the middle Q alpha, okay, And you exploit the fact that this polynomial is irreducible in Qx by Eisenstein's lemma. So this degree is 3. Okay, so it remains to evaluate this degree, but this degree. So remember, we have just seen that E is Q alpha omega, or if you wish, Q alpha extended with omega. Okay, so this is, let's say, if you call K Q alpha, yes, this is K omega over K. Now omega is a primitive third root of unity, so omega is a root of x squared plus x plus 1. The usual fact, I mean, omega is a root of s cubed minus 1, but this factors in this way, and clearly omega is not a root of this, so it must be a root of this one. And of course, so this degree is at most 2, but the degree is actually 2 because omega as omega is not in K, because K is Q alpha and is contained in the real numbers, whereas omega, as you know, is cosine of something plus I of something else. So omega is not a real number. So summing it up, this means that this degree is 6. So because this degree is 2, we just, next page, in case you reread the boards later. And so we have that this degree is 6. And since E is the splitting field of a separable polynomial, so this is Galois, okay? We are in characteristic 0, it's a splitting field, so it's a Galois extension. And so this means that the Galois group has also order 6. And remember that since E is also the extension of Q with these 3 roots of s cubed minus 2, an element of the Galois group is determined by the action of the Galois group on these 3 elements. The Galois group permutes this because these are root of a polynomial with coefficient in Q. So Galois, this map, say, the natural map, sending this to the, say, permutation group on the 3 elements alpha, alpha omega square. This map, which is a morphism, this map is injective, meaning that an element of the Galois group is completely determined by what it does on the 3 elements, because E, as I said, is generated over Q by these 3. And this permutation group is S3. This is isomorphic to S3, which is 6 elements. And this has 6 elements as well. So this means that the Galois group, I'll write it like this, is isomorphic to S3, meaning that within the Galois group, you have elements permuting these 3 elements in any possible way, okay? It's just a matter of orders. Good. So in particular, since this is amorphous to S3, we will have an element G in G, okay, which corresponds to a 3 cycle, which is the 3 cycle alpha, alpha omega, and alpha omega square, okay? So this means alpha goes to alpha omega goes to alpha omega square, and alpha omega square goes to alpha. Moreover, recall that in the proof of the lemma last time, we used the term C for the complex conjugacy. And C, of course, what it will do, it fixes alpha. Remember that alpha is a is an element, a real, I mean, it's the real root of its cube minus 2. So this exchanges alpha omega and alpha omega square, because alpha omega is the usual stuff with third roots of unity. Omega is in the complex plane, omega is here, omega square here, and they are conjugate, okay? They are symmetric with respect to the real axis. Good, so this is the fact. And it's quite clear that GC is different from CG. It's something we know very well in the symmetric group, that a 3-cycle and a 2-cycle do not commute. It's a standard fact. We normally write it as 1, 2, 3 and 1, 2 or whatever, 2, 3 in this case. But I mean, in general, we know that they don't commute. And the effect is the following, that so the result tells you that if you take an element and apply an element of the Galois group and then take the absolute value, this is the same as taking the absolute value and then applying the group element, the group element of the Galois group. We'll show that this is not the case here, and we'll do it as in the proof with squares, okay? So we consider, we want to show, we claim, so recall that G is this 3-cycle, in my particular case. We claim that alpha G square is different from alpha square G, okay? Well, since the absolute values are positive numbers, saying these two are different means also that they are different without the square, okay? So let's compute. So here you have alpha to the G, and recall G, I'll rewrite it here. G is the 3-cycle doing this, okay? So this is alpha omega, absolute value square, but the absolute value, of course, is multiplicative. So this is absolute value of this, absolute value of this square, and the absolute value of a root of unity is 1. Is 1, okay? And so this is absolute value of alpha square, which is actually alpha square, because alpha is a positive real number, okay? And so its absolute value is just itself. But what happens here instead? Well, let's see. So the absolute value of alpha is just alpha. So this is alpha square to which we apply G. And G sends alpha to alpha omega, okay? And G is an element of the Galois group. So it's a homomorphism of the extension E, a ring homomorphism. So this will be alpha G square. So this is alpha omega square, and this is, of course, alpha omega square. And so you see, on the one hand, you have alpha square, and here you have alpha omega square, two different things, okay? So the lemma we have seen depends very much on the fact, if you review the proof, that when this is abelian, any element G commutes with complex conjugation, okay? If you review the proof, you see that this is the critical step. Good, so with this observation, we can move to proving that a nonlinear character let me write chi for the reason you see in a second, vanishes on some element. It takes the value 0. And nonlinear means chi1 different from 1. Okay, a linear character is a character whose value on 1 is 1, meaning it corresponds to a one-dimensional representation. So that's the reason why I named chi, because I want to write chi1 different from 1. Okay, so we'll prove this. The value, sorry, this takes the value 0, I meant. Okay, so we start with a lemma, which is really the core part of the proof. So we take G, a cyclic group over the N. Okay, and then we write S, which is the subset of G. Okay, let's say G in G, such that G is order exactly N. And we know from algebra, from even first year algebra, that of course there is at least one element because G is cyclic over the N, so it has an element over the N, but we know that the order of S is equals the what do you call it? Euler function of N. Actually, this is the definition we usually give. Now, suppose chi is, let me see whether I need it to be reducible. No, so far I don't think I need it to be reducible. Yes, I don't need it. So let chi be a character of G, which is different from 0 for all elements of S. Sorry, I have to add irreducible. Okay, an irreducible character. Let me circle in red because this is important. Otherwise, it is not true. I mean, this result holds for any character, this intermediate result, this lemma, but this one requires this to be reducible. So suppose you have a character which is different from 0 for all S in S. So you have a cyclic group, and you take the elements of the cyclic group over the N, and you assume there is a character which is non-zero for all elements over there exactly N. And then the claim is that if you take the sum over S of the square of the absolute value of the value of chi on S, so this is the sum over S, this is at least the order of S. Okay. Perhaps I'll note here on the side. No, well, no, okay. No, that's I'll make this observation later. Good. So this is what we have to prove. We have to prove that you have a cyclic group. We have taken the elements over the N. You've taken a character of G which does not vanish on these elements. We'll use them then by a proof, not exactly by contradiction, but by counterposition or whatever it is. And we want to prove that this sum is at least S. Okay, proof. And I mean, we are going to apply the lemma. So we take E over Q to be the splitting field say inside the C of the polynomial x to the n minus 1. So remember that the group we are sorry, the group we are discussing is a cyclic group of order n. This is the same n, okay? And let H, the letter G being already taken, be the Galois group of V over Q. So perhaps we could recall at this stage that this Galois group, let me see, no, well, we'll mention this later. So what does an element H over H do? Well, since it's an element of the Galois group, it will permute the roots of x to the n minus 1. And in particular, it will take an nth root of unity of unity. I mean, this is something that you have seen in Galois group, in the course of Galois group, an nth root of unity omega to a power omega to the m for m coprime. So for M coprime, for M coprime to N. So, I mean, this group, we'll mention here that this group is isomorphic to the group of units of Zn star. So this is the group of invertible elements of the ring Z over Nz. Say this is true. You prove this by noting that if omega is a primitive nth root of unity, then of course the Galois group sends it in a primitive nth root of unity, and so primitive means an element exactly over the n, and for omega to the n to be exactly over the n, you need this condition. So this is true for a primitive root, a primitive nth root of unity, and every nth root of unity is a power of a primitive one. Okay, the primitive one means that the group of the roots of xn minus 1 is generated by omega. So this fact is true for every nth root of unity. Okay, and the group then will H will be isomorphic to this, because after all it's just the multiplicative group of these exponents. Note in particular that this is abelian. That's where our previous lemma, the lemma we discussed at the beginning of the lectures, come in. Okay, so fine. So let's consider an element S in S. So what's chi of S, chi being this character? Well, this will be a sum omega 1 plus omega 2 plus omega, say, t for some t, where this omega I for some nth root of unity. Not necessarily primitive roots of unity, but some of them will have to be primitive, but nth root of unity omega I. And the reason is the usual one, because rho of S can, rho being the representation affording chi, rho of S can be put in diagonal form, and since S has order n, the elements of the diagonal have to be nth roots of unity, okay? Because they satisfy the same condition that raised to the nth power, they give 1. So that's chi of S. And this follows that if H is this element of the Galois group taking omega to the m, this will imply that chi S to the H will be, well, natural enough, omega 1 to the m plus omega t to the m, okay? Because that's what H does. But we also know that if you take m coprime for n with n, then the map G going to Gm is a permutation, actually an automorphic, but a permutation of G. Remember, G is cyclic of order n. Because for the same reason that we were mentioning while discussing the roots of unity, remember there is a formula that tells you in particular that if G has order n, okay, then the order of G to the n is n divided by the greatest common divisor between m and n. If this is 1, this means that this has also order n, okay, because m is coprime. So this is a permutation of G. And so this means that if S is in S, then what's rho of S to the m? because, yes, let me see. I call it G. Okay, let me write S, sorry. So for S in S, okay? Let me, sorry, I modified, I should have, okay, so these were G, which have become S. So if S is in S, just for consistency, then this is a morphism, so this will be rho to the S, S to the M. Rho S, remember, was omega 1, omega t to the N, to the M. And of course, this being a diagonal matrix, there's nothing of diagonal means these are zeros. You have omega 1 to the M, omega t to the M. And you see that this is exactly what we have found. We have found that the character of chi of S to the M is exactly you see, it's exactly the image of the character, or the value of the character on S under H, okay? Because H sends roots of unity omega to omega M, and the same does that map, okay? So this is exactly chi S to the H. Because the two actions, I mean, taking powers on S or taking, applying H on the value of chi of S do the same thing. I mean, H, I mean, this is simply the map that sends S to SM, the map on S. A permutation of, sorry, once more. Permutation of S, okay? Yes, it's also a permutation of G, but let's say SG is cyclic. This is what interests me. Okay, so we have this. Why is this important? Because, and again, because on the one hand, we have the map that takes an element to the power, the nth power, and on the other hand, this does the same, an element of the Galois group does the same to the nth roots of unity. Okay? And good. Now, by the lemma, since the Galois group is abelian, remember, it's isomorphic to the group of units of this ring, we will have that for alpha in E and H in H, we have the result that did not hold in the example we saw, that if you take an element alpha, this time this is a generic element, alpha is not the third root of anything, and you take the squares, because this is what interests me, you'll have this. So you can take the H inside. The reason is because here we are taking the conjugate, the complex conjugate, I'll say. Good. Now, consider the product for over S ranging in S of the squares of these character values, okay? Claim this is invariant under H, the Galois group. And the reason why this is so is that chi S is in E. Recall E is the splitting field of the polynomial xn minus 1, and the value of chi, S is here, is a sum of nth roots of unity. So when you apply, let's take one factor, okay? Just one factor. And we apply H. By the result we have just quoted, okay? Since this is in E, we can take the H inside, okay? But we have just seen that that applying H to chi of S is exactly the same thing as applying chi to a power S of m, which is still in S, okay? And this is another factor in the product. Okay? So this proves that this is invariant under H. So we see here we have used the lemma, okay, plus this fact that that the action of H here correspond to taking powers on elements of our cyclic group, okay? So this is invariant under H, it means it's fixed. So in other words, this element, so this element is fixed by all H in H. And this is the Galois group over Q. Because applying H just permutes the factors in the product, okay? H just permutes the factor. Okay, because S to the M would be another element of S. Okay, so you apply H and you find another factor here. But then this means, since the extension is a Galois extension, again, because it's a splitting field in characteristic 0, it's Galois, this means that this element is in Q, because I mean, Galois means that the fixed points of the Galois groups are exactly the character, the elements of Q. But remember that, we have seen this several times today. The value of chi of S is the sum of nth root of unity, which are algebraic integers, and their sum, remember, sum and products of algebraic integers are algebraic integers. So so the chi S are algebraic integers, okay? But so my claim is that, this product, I mean, my claim is that this is an algebraic integer. To see it correctly, note that this is just chi S conjugate, okay? That's the absolute value squared, okay? And these are algebraic integers. A sum of algebraic integers. I mean, this is a sum of nth roots of unity. Let's do it explicitly. So these are nth roots of unity. What's the conjugate? Well, are conjugates, but recall that these are just the inverses. So again, nth roots of unity. So these are the nth roots of unity are algebraic integers. Their sum are algebraic integers. Their product is algebraic integer. Okay. So this, because we proved that sum is product of algebraic integers. So this is an algebraic integer. And we have seen that it is in Q, okay? We just see here that it's in Q, okay? Because it's fixed by the group. And this is an easy fact, but it's very important. This means that this is an integer. And actually, since this is absolute value square, I mean, this is actually a natural number, okay? Okay, so let's say is in N. Now, my natural numbers, I mean, since I'm an algebraist, include 0, but remember that the assumption is that chi S is different from 0 for all S. This follows that this is a positive natural number, so this is greater than or equal to 1, okay? it cannot be 0 by assumption. I mean, it's an integer. It's positive. It's not negative because, I mean, the absolute values are not negative here. I'm even squaring them. So it's a natural number, and then it's not 0 by assumption, okay? So you have this greater than or equal to 1, and then now you use the inequality that tells you that, okay, the inequality that tells you that if you take an arithmetic mean, okay, so this is the arithmetic mean of these values. This is at least this greater than or equal to the geometric mean. It's the inequality between the arithmetic and the geometric mean. And the geometric mean, well, it's the multiplicative version. So here you have the product of the squares, and then you take instead of dividing, you take the root. And this is just greater than or equal to 1, okay? So you see, we have obtained the desired result because we have obtained that this arithmetic mean is at least 1 because this factor is greater than or equal to 1, and this won't be altered by taking a root. And so, I mean, if you take the order of S to the other side, you'll find that this is greater than or equal to S, okay? Now let's see whether we can finish. Yeah, we are probably in a position to finish our result, and then here's the theorem, which is the theorem of Burnside, which we could have used to compute speedily some character tables, for instance, of S3 and so on, but then we did it anyway. So let G be a finite group. And chi an irreducible character. This is important. As you'll see, this will play an important role. I mean, we're going to use the orthogonality relations, okay? If chi is non-linear, that is chi1 is different from 1, then there is G in G, such that chi of G is 0. For the proof, we'll prove the counter positive or whatever it's called. Well, whatever. We are proving that we prove that if chi of G is different from 0 for all G in G, then chi of 1 is 1. That is, chi is linear, okay? It's not a proof by contradiction, it's just that we prove that if you, that the negation of this implies the negation of this. Good, how do we prove this? Well, we consider an equivalence relation on G defined R, let's call it R, so we won't particularly be using the letter. Well, we say that A is in the relation R with B if and only if A and B generate the same subgroup, cyclic subgroup, okay? So if A is an element of this group G, this time the group is arbitrary, is an arbitrary finite group. Its class A, class with respect to this relation, will be given exactly by the element S of the cyclic group is generate, okay, which have the same order as A. Okay, because to generate this subgroup generated by A, B has to have the same order as A, okay? And so we see that we are, this is exactly the object, capital S of the previous lemma, okay? So if the order of A is n, so we are talking S, the element, so this is cyclic group of order n, okay? Such that S is order n. So this is exactly the same object that we had in the lemma, okay? So the idea what is we have this is clearly an equivalence relation, okay? And these are the classes, and we know that the equivalence classes form a partition. So we have that consider, well, first of all, chi is irreducible, okay? And this means that the inner product is 1. But what's this inner product? This is 1 over G. And then we are summing over G, chi G conjugate, or chi G inverse, which is the same. And this is nothing else that the absolute value squared, okay? This is the definition, okay? So if we consider, okay, and this is 1, okay? So this means in particular that the order of G is equal to the sum for G or in G of chi G absolute value squared, okay? I have simply taken this and multiplied by the order of G, okay? So this stuff multiplied by the order of G will be G. And we split this sum over the conjugates, over the equivalence classes. So S we runs over the equivalence classes of the relation R. And then we have the sum S in S of chi S squared. But the previous lemma, as I said, the equivalence class of an element A under this relation is nothing else than the set of elements in a cyclic group of order n, if n is the order of A, which have order n, okay, same order of A. And then this means that if you consider the previous result tells you that this is greater than the sum over all the equivalence classes of the order of S. This is at least the order of S. And since you are summing over the equivalence classes, okay, which are the equivalence classes are a partition of G. So if you sum over the equivalence classes or all the S, you get simply the order of G, okay? Because the G is the disjoint of union of the equivalence classes. So if you sum the orders of the equivalence classes, you find the order of G. So you start with the order of G, you add a greater than or equal to, and you obtain the order of G. So this means that all inequalities, I mean, we have used this inequality, that if you have such a class S, this is greater than or equal the order of S. But the fact that we have obtained an equality means that for each class S, you have equality here, okay? It cannot be stricter than, greater than. So for each class S, which is the class of a particular element, we have the sum over S of K, for S, yes, S in S, okay? I have just added this because otherwise there was some hint of confusion, is the order of S. And now it's simply a matter of noting that take as a particular case A equals 1, okay? So what's the class of A, the class S? This is simply, well, it's the set of elements. We generate a group generated by 1. So there's only one element, okay? It's the set of elements of order 1, which is only 1. Okay? Again, because the relation, let me repeat it here, the relation ARB means that the group generated by A is the same thing as the group generated by B, and the group generated by A in this case is just 1. Okay, so B has to be 1. And what does this relation in this case tells you? In this particular case, it means if you sum over the elements of S, but there's just one element, this is the order of S, which has just one element. Okay? And so the square, the degree of a character is a positive integer, and its square is 1. So this means that we have obtained that chi of 1 is 1. Okay? That is, chi is linear. And my assumption was that you had a character which does not vanish. Okay, that's why we could apply the lemma, and we have found exactly that the character is linear. So we have this sequence of equalities with the inequalities greater than or equal to. Since you have obtained the element you start with, these are all equalities, and you just have to look at the particular case of the class of 1 to obtain that the character is linear. Okay, that's all for today. We'll continue tomorrow with more algebraic integers. Thanks for listening.